Hello, and welcome again to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today, we're going to be taking a second look at conditional probability and the concept of statistical independence. So let's review a bit and talk a little bit about the basic concept of conditional probability. Conditional probability begins with this statement. It is not one of the axioms of probability. It is nevertheless axiomatic. It's not something I can prove. I hope it's something you will repeat to yourself time and time and time again until you convince yourself that it's correct. We begin this way. The probability of A and B, probability of events A and B occurring simultaneously equals the probability that event A occurs if event B occurs times the probability that event B occurs. The probability of event A and B occurring simultaneously equals the probability that A occurs if event B occurs times the probability that event B actually does occur. A couple other different pieces of notation we use to indicate the conjunction. Probability of A comma B. This comma implies the word and. It's a conjunction. And another way, using set theory, is probability of event A intersect B. All right? The intersection of A and B is that collection of events which are both in A and B simultaneously. So if any of the events that occur in the intersection occur, both A and B occur simultaneously. So it's handy for us to rewrite our conditional probability relationship this way so that we can use set theory notation. We write a probability of A intersect B equals the probability of A if B times the probability of B. And you'll recall from our prior discussion that this vertical bar implies an if. So that's the way we're going to write our conditional probability relationship for most of the rest of the semester. Okay. Let's rearrange that just a little bit. Let's just remind ourselves. Probability of A and B equals the probability of A if B times the probability of B. Let's rearrange this just a bit, and we'll find that the probability of A if B equals the probability of A intersect B divided by the probability of B. This relationship here is a conditional probability. In the numerator, we have a joint probability, probability of A and B occurring simultaneously. And in the numerator, we have what's known as a marginal probability. All right. If we rearranged A and B in our initial statement at the top of the board, we could write something like this. We could say probability of B if A equals probability of B intersect A divided by the probability of A. Well, we know that A intersect B equals B intersect A from the commutative property of set theory. So the numerators of these two relationships are exactly the same. The numerators are the same in these two relationships, but the denominators are not the same. The probability of A and the probability of B are not necessarily equal. So I can conclude in general probability of A if B does not equal probability of B if A, in general. There are some circumstances where that might be the case, but in general, that is not the case. All right, let's make some observations. If A and B are mutually exclusive, means they share no common elements, or A intersect B equals the empty set, then probability of A if B, which equals the probability of A intersect B divided by probability of B. That's the probability of the empty set divided by probability of B. Probability of the empty set is exactly 0. So the probability of A if B is exactly 0 if A and B are mutually exclusive. Similarly, if A and B are mutually exclusive, I could also write probability of B if A equals 0 if A intersect B equals empty set. All right? Okay? Another observation. If A is a subset of B, then clearly A intersects B at A. If all the elements in A are in B, then A intersects B at A. And probability of A if B equals probability of A intersect B divided by probability of B, which is probability of A divided by probability of B. That's one piece. And probability of B if A equals probability of A intersect B divided by probability of A equals probability of A divided by probability of A is 100%. All right? So remember, an event occurs if one or more outcomes in that event occurs. If all of the if all of the outcomes in A are also in B, then if A occurs, B has to have also occurred. If A is a subset of B, then if A occurs, it's 100% likely that B also occurs. There. Okay? All right. Let's do an example. Let's do an example. This is a little different than the example we've done in the past. We're going to toss a single fair coin twice. We'll toss a single fair coin twice. Previously, we've done an example where we tossed two fair coins once. This time we're going to toss a single fair coin twice. And we're going to observe heads and tails. And here's the question. Given that at least one head was obtained in the two tosses, given that at least one head was observed, what's the probability of tossing? What is the probability of tossing two heads? All right, so my chance experiment is toss one coin twice. Toss one coin twice and observe heads, tails. Sample space has four equally likely outcomes. Head one, head two, tail one, tail two, head one, tail two, tail one, head two. Event A is the event that we get at least one head in two tries. Head one, head two, head one, tail two, tail one, head two. One head in two tosses. And event B is head one, head two, heads on both tosses. All right? Well, the question that's been asked of us is this. Given that at least one head was observed, meaning that event A occurred, what is the probability of tossing two heads, meaning that event B occurred? So we've asked ourselves, what is the probability of tossing two heads, given that at least one head was observed? And that equals the probability of A intersect B divided by probability of A. The marginal probability that goes in the denominator is always whatever is on the right-hand side of the if bar. Okay? So, let's work that out. For this example, clearly, the probability of A is 3 chances out of 4. Event A had 3 of the possible outcomes in my sample space. And there are 4 possible outcomes in the sample space. Probability of B is 1 chance out of 4, 0.25. And the probability of the intersection, A intersect B, is 1 chance out of 4. Right here is where A and B intersect. Heads, heads is where the events A and events B occurs. That's 1 chance out of the 4 possible in my sample space. So the probability of the intersection of A and B is 1 chance out of 4, 25%. Plugging that all in, I get probability of B if A equals probability of A intersect B divided by probability of A. That is 1/4 divided by 3/4, and that's 1/3. All right? B is a single outcome event, and that one outcome is one of the 3 possible outcomes in event A. Let's go back and look at that. Event B is a single outcome event. There it is. And that outcome is one of the 3 possible outcomes in event A. So if A occurs, it's 1 chance in 3 that B occurs. That's what that means. Okay? That's what that means. All right. Let's do another example. What I'm going to do is I'm going to randomly select a number from the integers from 1 to 100. Randomly select an integer from the integers between 1 to 100. And let's define some events now. Event A2 is going to be all integers A sub I. I represents the integer value, divisible by 2 without a remainder. All right. Event A sub 2 is going to be the collection of all integers, A sub I, where I represents the integer value. A2 is the collection of all possible integers, A sub I, that are divisible by 2 without remainder. A3 is going to be all A sub I divisible by 3 without remainder. And A5 is going to be the collection of integers A sub I, where little I represents the integer value, that are divisible by 5 without remainder. And the question we want to answer is, given that my integer, a sub I, is divisible by 2, what is the probability what's the probability that a sub I is also divisible by either 3 or 5 without remainder? All right. 3 or 5 without remainder. So in effect what we're asking is this in conditional probability terms. We're saying the probability if the integer that I select falls in event A2, meaning that it's divisible by 2 without remainder, what is the probability that it is also divisible by either 3 or 5 without remainder? The union symbol represents an or. It can be divisible by 3 or 5, meaning it lies somewhere in the union of those two events. You remember that the intersection represented the word and represented a conjunction. It was both in A and B if it lied within the intersection. The union operation represents an or. So this is the question that we want to answer. The probability that the integer I select, little a sub I, lies within A3 or A5, given that it also is divisible by 2 without remainder. All right, so let's work that out. Oops. From the definition of conditional probability, we have probability of A3 union A5 intersect A2 divided by probability of A2. This is from definition of conditional probability. That's from the definition of conditional probability. Expand this out a bit. I want to get the probability of A3 intersect A2 union A5 intersect A2 divided by probability of A2. This, to get to this step, I applied the distributive property. Applied the distributive property inside of the probability relationship. All right. And then I'm going to expand this one more time. I don't know if the union of these two events in the last step are mutually exclusive, so I can apply this relationship, probability of A3 intersect A2 plus probability of A5 intersect A2 minus probability of A5 intersect A3 intersect A2, all divided by the probability of A2. Okay? And here in the numerator, I've applied the relationship we derived earlier. Probability of A union B equals probability of A plus probability of B minus probability of the intersection, if they are not necessarily mutually exclusive events. All right? Now, I'm going to put a star beside this relationship because I'm going to come back to it in just a minute and make a further observation. Let's go ahead and finish the problem. Well, the event A3 intersect A2 equals that collection of outcomes A sub I, which are divisible by 6 without remainder. A5 intersect A2 is the collection of outcomes, a collection of integers, A sub I, that are divisible by 10. Without remainder. And A2 intersect A3 intersect A5 is the collection of integers that are divisible by 30. Without remainder. The probability of A3 intersect A2 is 16/100ths. What that means is there are 16 integers out of the 100 between 1 and 100 that are divisible by 6 without a remainder. There's 16 integers divisible by 6 without a remainder somewhere between 1 and 100. I'll let you work that out yourself. The probability of A5 intersect A2 is 10 chances out of 100. Probability of A2 intersect A3 intersect A5 is 3 chances out of 100. There are only 3 integers that are divisible by 30 without remainder between 1 and 100. And then finally, probability of A2 is clearly 50/100ths. All right, there are 50 even integers between 1 and 100. All right. So, therefore, the probability of A3 union A5 given A2, it's divisible by, if it's divisible by 2, it is also divisible by 3 or 5 at the same time. That's 16 plus 10 minus 3 over 50. That's 23 chances out of 50. It's about 46%. As with many of the examples that I'm going to do for you, the final result is not nearly as interesting as the process. All right. Let's re-examine this relationship just a bit, the relationship with a star. Take a look at that again. What we see is three different conditional probability relationships on the right-hand side of the equal sign. All right? Each of those relationships can be written as a conditional probability. So let's rewrite this. My starred relationship. My starred relationship can be rewritten this way. Rewrite that starred relationship that way using the definition of conditional probability. In general, then, I can write this. Probability of A union B if C equals probability of A if C plus the probability of B if C minus probability of A intersect B if C. That's a general relationship. We may have need of using that relationship from time to time through the semester. So just hang on to it. All right. Let's also now take a second look at the notion of statistical independence. Statistical independence. So let's write down our statement of conditional probability. It says a probability of A and B equals probability of A if B times probability of B. This is my definition. That's the definition of conditional probability. So, referring back to our prior discussion on statistical independence is if A does not depend in any way on B, then probability of A if B is just probability of A. Right? So, I can rewrite this. Probability of A if B equals probability of A intersect B divided by probability of B. Just a rearrangement of my definition of conditional probability. If A and B are statistically independent, this relationship is just equal to the probability of A. or probability of A intersect B equals the probability of A times the probability of B. That is a very important relationship. This, in fact, is taken as the definition, if you will, of statistical That's more or less the mathematical definition of statistical independence. By that I mean if the probability of the intersection equals the product of the marginal probabilities, then A and B are statistically independent. Let me say that again. If the probability of the intersection equals the product of marginal probabilities, then events A and B are statistically independent. All right? In general, I can expand this to any number of events. So in general, if I have K events, and they are all mutually statistically independent, meaning that none of them depend upon one another in any way, shape, or form, then the probability of the collective intersection equals the product of marginal probabilities. All right, that's just a general statement. All right. Okay. Let's do an example. And this is going to be our random experiment. My experiment is going to be to toss 2 fair dice and add up the number of spots that are facing upwards. So toss 2 fair dice and counter add the number of spots up. Okay? Now count the number of spots up. My sample space is going to have 36 possible outcomes. I should say I'm going to toss 2 fair 6-sided dice. Toss 2 fair 6-sided dice. My sample space is going to have 36 possible outcomes. And those outcomes are represented in this table. All right. don't worry too much about the title to this table. We will get into the notion of random variables and random value assignments a little bit later on. I'm going to make this table available to you as a downloadable PDF for you to use and to write on. But there's 36 possible outcomes. If I roll snake eyes, I get 2 spots up. If I roll double sixes, I get 12 spots up, and everything in between. I'm going to somehow assume that my dice are distinguishable from one another. I'm going to assume that my dice are somehow distinguishable from one another and that they're named dice 1 and or die 1 and die 2. All right. Event A is going to be the event that I have a total of 7 spots up. Event A is the event that I have in 7 spots up. That's 6 possible outcomes. 6 possible outcomes. If I look at my table, 7 spots up. That's event A. Event B is going to be the event that the sum of the spots is 6. All right, and there are going to be 5 outcomes. Going to be 5 outcomes. 6 spots up is that outcome, or that event. And event C is going to be the event that die 1 shows 4 spots. And once again, here there are 6 outcomes. There's 6 possible outcomes. What color have we not used? Green. Die 1 shows 4 spots up. There is my event C, and you'll notice that event C and B intersect one place, and event C and A intersect in one place. Okay. We're going to assume that we use the following notation. A sub I j equals I plus j, and this is an outcome. This is the outcome designation. It's one of the values in the table that I've been showing you, where the outcome is the sum of the spots up, and where I is spots up on die 1, and J is spots up on die 2. Okay? So there are the 36 A sub I J values. All right, let's start working out some math. A intersects C at exactly one event, or one outcome. And that is A sub 4, 3. Likewise, event B intersects C at event A 4, 2. Probability of event A is 6 chances out of 36, as we've seen. 6 ways to get a 7. So the probability of event A is 1/6. The probability of event B is 5 chances out of 36. And the probability of event C equals 6 chances out of 36. Event C was the event that die 1 showed 4 spots. There's 6 ways for that to occur. So, probability of A intersecting C is 1 chance out of 36. And that equals probability of A times the probability of C. Probability of A is 1/6. The probability of C is 1/6. 1/6 times 1/6 is 1/36. This means that A and C, by definition of statistical independence says that the probability of A intersect C equals the product of marginal probabilities if A and C are statistically independent. So, A and C are statistically independent. Basically what this means is that a sum of 7 spots, that's event A, a sum of 7 spots is possible for any value that shows, any number of spots that shows up on die 1. Say that again. They're statistically independent because the sum of a sum of 7 total spots up is possible for any value of spots up on the first die. All right, event A is the event that 7 total spots are up. Event C is the event that there are 4 spots up on die 1. So here, a sum of 7 total spots up is possible for any, not and, any value of spots up on die 1. However, probability of B intersect C equals 1/36. Once again, there's only one outcome in event B intersects C. But this is not equal to probability of B times the probability of C. 536 times 1/6 is not equal to 1/36. B and C are not statistically independent. All right? A sum of 6 spots up total is not possible for all values of spots up on die 1. All right? Six total spots up. Six total spots up cannot occur for all values of spots up on die 1. That means events B and C are not statistically independent. Okay. Let's make some more observations. The probability of C if A equals probability of A intersect C divided by the probability of A. And remember, event A is 7 total spots, and C is 4 spots on die 1. Okay. This is 1/36 divided by 1/6, which is 1/6. The probability of having 4 spots up on die 1 if I know that there are a total of 7 spots is 1/6. The probability of C if B, this is 6 spots total, equals probability of B intersect C divided by probability of B. That's 1/36 divided by 5/36. That's 1/5. 1/5 is greater than 1/6. All right. What we find is if we know that 6 total spots are up, if we know that there's 6 total spots up, it's more likely that there are 4 spots on die 1 than if we know that there are 7 spots total. Okay. Let's do another example. If A and B are independent, and by the way, for most of the rest of the semester, I'm not going to say statistically independent. I'm just going to say independent. If I say independent, I mean statistically independent. So if A and B are statistically independent or just independent, show that A and B complement are also statistically independent. So we'll start by writing down just a simple true statement. Probability of A equals probability of A intersect B plus the probability of A intersect not B. That's just a true statement. A, in any event A equals A intersect B union A intersect not B. And the union of the probability of disjoint sets is just simply the sum of probabilities. All right, let's rearrange this just a bit. Probability of A intersect B naught equals probability of A minus probability of A intersect B. That's just simply a rearrangement. On the right-hand side now, excuse me, that's not an equal sign. That's a plus sign, or a minus sign rather. If A and B are independent, which we're assuming that A and B are independent, then the right-hand side of my relationship down here can be written as the product of marginal probabilities. Now I can just factor it out. Factor out the probability of A. Just algebra to get me to there. But from a relationship we derived earlier, 1 minus the probability of B is the probability of B complement. So if A and B are statistically independent, we see that A and B complement are also statistically independent because the probability of the intersection can be written as the product of marginal probabilities. So if A and B are statistically independent, then A and B complement are also statistically independent. One final observation for the day. If try that again. Events A and B cannot be both statistically independent and mutually exclusive. Assuming that neither A nor B are the empty set. All right. Events A and B cannot be both statistically independent and mutually exclusive under the assumption that A and B are neither the empty set. So if they are mutually exclusive, the probability of the intersection equals the probability of the empty set, which is 0. If they're mutually exclusive, that means that the events A and B intersect nowhere, so the probability of the empty set is 0, whereas the statement of statistical independence is as follows. Probability of A intersect B equals the probability of A times the probability of B. All right? The point of all of this being that it is not a true statement to say that if events A and B are statistically independent, then they have no common elements. That is not true. So Knowing that two events are statistically independent does not imply that they are mutually exclusive and share no common elements. Common outcomes. Knowing that two events are statistically independent does not imply that they are mutually exclusive and therefore share no common elements. Please don't confuse statistical independence with the notion of mutual exclusivity. And that brings us to the end of today's lecture. I apologize, it is a little bit long, but the notions of conditional probability and statistical independence are quite deep. It's something you need to spend a fair amount of time with and contemplate at length. As always, if you have any questions about what we've done today, please feel free to contact me at your earliest convenience, and I will try to clarify things as best as I can. Have a good evening. Bye-bye.